Welcome to The Explainer. Have you ever really thought about how that apple you ate for breakfast becomes the energy for your morning run? Or, get this, how it powers the very thoughts in your head? Well, today we're diving deep into the incredible chemical engine that runs inside every single living cell. This is the chemistry of life itself.
So here's our game plan. First up, we're going to tackle why any of this matters. Then we'll get into the basic rules of energy that all life has to play by. From there, we'll follow a single sugar molecule as it gets split for fuel, see how that plugs into the cell's main power grid, and finally, we'll zoom out to see how this tiny molecular dance changes everything from medicine to the food we eat. It's an amazing question, right? How does that one piece of fruit fuel everything you do, from moving your muscles to just thinking? The answer is hiding in plain sight, in this beautiful, complex dance of molecules at the heart of a science called biochemistry. Okay, so what is biochemistry really? Well, put simply, it's the science that looks at all the chemical reactions happening inside living things. But it's not just a bunch of random facts, it's the actual logic behind what it means to be alive. Think of it like this. It's the bridge that connects biology and chemistry. It asks the really big questions, like, how do a bunch of lifeless molecules come together, start interacting, and create this incredible symphony we call life? From a tiny bacterium all the way up to you.
All right, so to really get how life works, we have to start with the fundamental rules of energy. And these laws don't just apply to things like cars or power plants. They control every single chemical reaction happening inside your cells, right this second.
The first law is pretty easy to get your head around. You can't make energy out of nothing, and you can't destroy it. You can only change its form. But that second law, that one's a game changer. It says that the universe, left to its own devices, always gets messier. It naturally moves from order to disorder, or entropy. And that is the perfect way to picture entropy. I mean, think about it. Your body, with all its incredibly ordered and complex systems, is in a constant, energy-guzzling war against this universal pull towards chaos. Just staying alive, from a biochemical standpoint, is an act of rebellion against the universe's tendency to just fall apart. So, how do our cells figure out which reactions are going to work? Well, it all comes down to balancing these three things. Think of it like a budget. Enthalpy is the total amount of money you have. Entropy is like this unavoidable chaos tax. The universe is always going to take its cut. What's left over, that's Gibbs free energy. That's the actual usable cash you have to get things done. It's the only number that really matters for powering life.
And this is the master equation that brings it all together. Now, you don't need to memorize it, but you do need to know this one simple rule. For a reaction to happen all by itself without being forced, the change in Gibbs free energy, or delta G, has to be negative. A negative delta G is the universe giving the green light. It's the chemical permission slip that allows life to happen.
Okay, theory's great, but let's see this in action. We're going to follow one molecule of sugar on the very first part of its journey to release energy. And this is an ancient 10-step process called glycolysis. The name literally says it all. Glycus for sweet, lysis for splitting. Sweet splitting. This is the universal first move for basically any cell that wants to get energy from glucose. It happens right in the main fluid of the cell, and it's so fundamental it doesn't even need oxygen. You can think of glycolysis like starting a business. You got to spend money to make money, right? Well, first you have the prep phase, where the cell has to invest a little energy to get the glucose molecule ready. Then you get the payoff phase, where the cell cashes in and gets its investment back, plus interest.
So the journey begins. Right out of the gate, this cell makes an investment. It spends one molecule of its energy cash, that's ATP, to stick a phosphate group onto the glucose. And this is a brilliant move. It not only gets the glucose ready for what's next, but it also acts like a chemical lock, trapping the sugar inside the cell so it can't just float away. A couple of steps later, the cell makes its second and final investment. It spends another ATP to add a second phosphate. This is the point of no return. It's the key commitment step. That glucose molecule is now locked in, and it is destined to be split. And here it is, our first return on investment. That original 6-carbon sugar is now split into two 3-carbon molecules, and each of those is now used to make an ATP. So 2 molecules, 2 ATP produced. At this point, we have officially broken even.
And the process wraps up with a grand finale. In the very last step, the leftover energy is captured to make 2 more molecules of ATP. So, We've taken one glucose, turned it into two pyruvate molecules, and made a total of 4 ATP in the process.
So what's the bottom line? This is the crucial part. We made 4 ATP, but remember, we spent 2 to get the whole thing started. That leaves us with a net profit of 2 ATP for the cell. Now, that's not a huge amount of energy, but it's fast, it's reliable, and believe me, it's just the beginning of the story.
Okay, so what happens to that pyruvate we just made? Well, if there's oxygen around, it gets a VIP pass into the cell's powerhouse, the mitochondrion. And in there, it enters the central hub of all metabolism, where the really massive energy payoff is about to begin. This is the citric acid cycle, sometimes called the Krebs cycle. The best way to think about it is as the cell's main metabolic roundabout. It doesn't matter what you ate, carbs, fats, or proteins. Once they're broken down, their parts all merge onto this one central pathway to be completely stripped of their energy.
And the cycle's job is brutally efficient. It takes what's left of our sugar molecule and just systematically rips high-energy electrons off of it. These electrons are like little packets of portable power that will be used later to make a ton of ATP. And the leftover carbon atoms, they're tossed out as waste. Yep, that's the very same carbon dioxide you're breathing out right now.
Okay, so we have been deep in the molecular weeds, right? From thermodynamics to these super detailed pathways. But let's pull the camera way, way back. Why is knowing all this so unbelievably important? Well, it matters because this isn't just theory in a textbook, it's the absolute foundation of your health. When these pathways go wrong, people get sick. And when we understand them, we can actually develop cures. This is where biochemistry becomes medicine. I mean, think about it. This knowledge is everywhere. When a doctor runs a blood test and checks your glucose levels, they're looking at the fuel for glycolysis. The entire field of nutrition is built on knowing what our bodies do with vitamins and minerals in these pathways. Every single drug you take is designed to interact with this cellular machinery. We even use this knowledge to make better crops to feed the world. It all comes back to these fundamental chemical reactions. So the next time you eat an apple, or take a breath, or even just have a thought, maybe you'll remember the incredibly elegant and efficient chemical dance that's making it all happen. Life is this constant story of energy exchange, taking it in from the world and transforming it to power the incredible reality of you.